Now it's time for us to introduce delta G into our electrochemistry chapter. The equation that we want is delta G equals negative NF E standard. This is the standard E cell that we've been calculating. N is the number of electrons being transferred in the reaction. And F is a constant. This constant is called a Faraday, after Michael Faraday, who was a scientist who studied electrochemistry. And 1 Faraday equals 96,485 coulombs, that's what that C is, coulombs per mole, which is 96,485 joules per volt mole, because that's what a coulomb is. It's a joule per volt. If you actually look on the list of values that the AP test gives you, they write this as 96,500. Your book will say 96,485. That's just a significant figures thing. Okay, so we've got this equation, delta G equals negative NFE0. Remember that we also know that delta G equals negative RT ln K. Remember that from the last chapter. What that means is that if we know the E cell, we can find the free energy. Note that little negative sign, because remember that a positive E is a spontaneous reaction, and a negative delta G is a spontaneous reaction. That's why we have that negative sign there. But if we've got E cell, we can find delta G. And if we've got delta G, we can find K. So if we know the E cell, we know the free energy, and we know the equilibrium constant. The next equation we're going to talk about is the Nernst equation. That's spelled N-E-R-N-S-T, Nernst equation. The Nernst equation is when you have your cell under non-standard conditions. You'll notice we have an E here related to an E0. The 0, of course, is standard conditions. Standard conditions for electrochemistry include a temperature of 25 degrees Celsius and 1 molar concentration of solutions. So if we don't have those things, we need the Nernst equation, where R is your basic gas law R, 8.3144. Temperature is, of course, in Kelvin. N is the number of electrons being transferred in the reaction. F is the Faraday that we just talked about. And Q is the equilibrium constant when you're not at equilibrium. This equation is based off of the delta G equals delta G standard plus RT ln Q that we learned about in thermodynamics. Now, a shortcut for this is if you're at 25 degrees Celsius or 298 K, the shortcut for this is E equals E standard minus 0.0592 over N log, L-O-G log, of Q. Now, Nernst equation is particularly useful when you have something called a concentration cell. A concentration cell is one in which you have the same substance on both sides of the cell, but one is more concentrated than the other. There's a picture in your book on page 874 of a nickel concentration cell, where they've got a nickel anode, a nickel cathode, but the nickel 2 plus solution in the anode is 1 times 10 to the negative third, and the nickel concentration in the cathode is 1 molar. Now, a concentration cell will run until the concentration in both sides is the same. At the anode, for this nickel cell, we have nickel solid going to nickel 2 plus, which is obviously aqueous, plus 2 electrons. That's the oxidation. And at the cathode, we have the reduction, which is nickel 2 plus, which is aqueous, plus the 2 electrons going to nickel solid. Now, obviously, the E reduction and the E oxidation are going to make 0. E reduction for this reaction is 0.28 volts. Well, the E oxidation is, of course, negative 0.28 volts. So 0.28 volts plus negative 0.28 volts is 0. You would think this cell would not run at all. But that's only E standard. We are not under standard condition. As I said, the cell will operate until the Ni plus in both compartments are equal. The oxidation is going to happen in the more dilute solution because that would make more Ni2 plus and thus lead to the cell concentrations evening out. So remember, when we're going to apply the Nernst equation to this, remember Nernst, we'll do the shortcut, E equals E standard minus 0.0592 over N log Q. Remember that when we do this, it's always, Q is always going to be the dilute one over the concentrated one. Always.